Hello everyone, my name is Navanga Afwa from Group 14, and I'm basically going to take you through the introduction, background of the study, problem statement, and the main objective of our project. That's an IoT and AI-Powered system for predictive waste management in urban Uganda. So for the introduction, realize that Kampala is growing so fast. So what does it mean? It means that there is more waste literally every day, and realize that currently it's 40 to 60% of waste that's collected that's literally causing health and environmental risks. So literally garbage collection is still manual and reactive. That goes ahead to mean that literally action is taken after problems occur. So to minimize this, we propose to come up with this project to go ahead and use IoT devices like smart sensors, look at the likes of cameras and computer intelligence to guide and predict problems before they actually happen. So literally looking at transforming urban sanitation into smart and sustainable system. So for the background of the study, realize that Kampala produces 2,000 to 2,500 tons of waste per day. And mostly it's organic waste. That's 92.1. So literally the city uses fixed routes, which are basically inefficient. And if you look at other smart cities around the world, they literally use AI or technology to manage their waste better. So our proposed solution is coming up with smart bins with sensors to detect how full they are. Like these bins literally have sensors for detecting how full the bins are. Then cameras to literally guide and identify what type of waste. Then for the solar power, sends data to so that trucks know where to go and when. So literally our solution is solar powered smart poles with ultrasonic sensors and cameras for real-time field level and waste type data. So our problem statement, like I've talked about, there are a lot of inefficiencies, resource misallocation, poor waste segregation, the data deficiency. Literally, garbage collection follows like fixed schedules, so bins can literally overflow. Like the schedules are literally many, so the moment they reach a certain location, like literally the bins have overflowed. So that's one problem. Then the other one, you look at sometimes garbage trucks go to the bins that are not yet full. So that's resource misallocation, literally in likes of fuel, labor. Then for the poor waste segregation, we look at different types of waste that are mixed together, which literally make recycling difficult. Look at plastics, metals, maybe they are mixed together and all that. And then authorities do not have real-time information about how full the bins are and what type of waste is literally inside them. So that's literally data deficiency. So literally the need is for a predictive IoT AI-driven system for dynamic routing, timely collection, and waste classification. So literally our main objective of this whole project is our main goal is to design a smart system that can go ahead and monitor where garbage is. Like it can monitor garbage bins automatically, go ahead and predict when bins are full, go ahead and sort waste automatically, and then guide the trucks to collect waste only when necessary. So literally we want a smarter, cleaner, cheaper way to collect garbage in urban Uganda. So that brings us to our main objective of designing and develop an integrated IoT and AI-powered system that enable predictive waste monitoring, automated classification, and dynamic route optimization for efficient collection in urban Uganda. That's it from me. Thank you.
Number one is like under the objectives we are aiming at, we have evaluating the system performance, which is going to be done through the like considering the aspects of accuracy, efficiency, even cost reduction. Yes. Then the other objective we are aiming at is designing Internet of Things, which is the smart poles, which will be equipped with multiple sensors, such as the field level, the field level sensors and cameras, which will be used for real time, like to collect real time data, which will be used for real time monitoring. Then the other objective we aim at is to develop machine learning models, such as the convolutional neural networks, which will help us under waste classification, which will be under the classifications of plastics, the glass, metal, even organic waste, and even to predict the overflow. Then the other objective is to build a web-based dashboard, which will be used by the organization, which is the KCCA, currently responsible for the waste collection and management, to collect and manage real data, visualizations, and even alerts. Then the last objective we have is to implement dynamic route optimization algorithms, which is basically VRP based for the collection trucks that will be collecting waste from various areas around. Then for the significance, of our research under KCCA, it will enable them to make quick decisions, which will help in reducing fuel costs up to a certain percentage and even optimize collection routes. Then for the residents, it will help encourage it will reduce environmental hazards, which involves odors, the pests, the blockages, and it will also improve the public health. Then for the policymakers, it will enable structured data sets, which will be used for evidence-based under urban planning and recycling policies. Then for the Uganda as a country, it will support smart city initiatives, digital transformations, and scalable duplication in other cities around the country. Yes, that's my part.
Good evening, everyone. My name is Benam Shadek, and I'll be taking you through the literature review and mainly focusing on the context and research gap. So, looking at the existing research, we see that Kampala's waste profile is quite unique, and why we call it unique is that its waste composition, it is 92.1% of organic waste, which is which has high moisture, and the existing recycling rates are low. So globally, IoT and AI systems are proven in waste management, but most studies are often theoretical and tested in developed regions. So the real gap lies in lack of low-cost integrated IoT AI systems, which are validated in resource constraints, real-world urban settings like Kampala, or also other urban cities like Makerere or Gulu. So the existing models where they mostly fail is in analyzing the high moisture or organic heavy waste systems, and this means that the current solutions fail the current systems need contextual adaptation rather than the theoretical one. Next, we are going to talk about the literature review, and mainly we are going to focus on the IoT and smart monitoring. So here the literature review we carried out, it guided our choices for hardware and AI. And for IoT sensing, ultrasonic sensors are widely used for reliable field level detection. And then the solar power enables off-grid operation, which ensures that in case power goes off from the main current, we have a reliable source or a backup that can be able to ensure that there is a continuous flow of data within the system. Then for waste classification, we have a lightweight CNN model, lightweight CNN models like MobileNet version 2, and this one is the mainly recommended one. And this one is because it is recommended because it balances accuracy and low computational demand, which is essential for edge development. But the main challenge is however, in balancing accuracy, latency, and power consumption in real time rather than the theoretical stuff. Then next, we're going to talk about the literature review in terms of optimization and data fusion. So the studies we carried about, they show that dynamic route optimization using algorithms like anti-colony optimization, SEO, and the genetic algorithms, they show that that fuel consumption can be reduced by 46%, and machine learning models like LSTMs can predict overflow events days in advance before it happens. So if we add data fusion, combining sensor, image, and GPS data, it creates a holistic view and decision making. But here's the main thing: we have to make sure that our studies don't stop in theoretical terms, but they are also applied in contextual or real world systems, because once it remains theoretical, it won't apply when it comes to time of testing. So that's it from me. Thank you very much.
My name is Chigobaza Fred, and I'll begin from where my colleagues have stopped. I'm going to take you through the research methodology. Research methodology for the three-tier architecture consisting of the smart pole hardware layer, the cloud server layer, and the central brain software layer. Data is first collected from the sensors at the bin, processed at the edge, and transmitted to the cloud, and finally analyzed to support predictive waste collection and route optimization. This structure ensures scalability, real-time monitoring, and efficient decision making. When you go to data collection and smart pole design, here data collection is done using a smart pole installed near waste bins. We use a ultrasonic sensor to capture waste images and GPS to track the bin location. Then we had two Arduinos, whereby Arduino boards, one handles sensors while the other manages communication and processing. But then we had a solar powered system that ensures continuous supply of power within the urban environments. Then when you go to data pre-processing, here before analysis, collected data is pre-processed to improve accuracy. Then for image data, images are resized, normalized, and augmented to improve the performance of the classification model. Then when we go to communication architecture, here when we talk about communication architecture, communication within the smart pole is achieved using the 1.2c protocol, which allows low power data exchange between the two Arduino boards. Then for external communication, a GSM or a 4G module sends data to the cloud in a JSON format using the HTTP requests. Then after here, the cloud then exposes the data through the RESTful APIs back to the dashboard for real-time monitoring. Then when we go to machine learning and analytics engine, here the analytics engine applies machine learning to classify waste types and predict the bin overflows. We use the VGG19 deep learning model trained on both public and locally collected datasets to classify waste images. Then we have Edge AI is implemented using TensorFlow Lite to allow on-device inference. Then for prediction, bins are flagged when fill levels exceed 80%, enabling waste collection. When we go to central brain and dashboard, the central brain hosts the system dashboard and analytics logic. It displays real-time bin status, then using color-coded alerts, historical trends, and we have waste composition charts. Once bins are flagged as full, the route optimization model calculates the shortest and the most efficient collection route to be used by the people collecting rubbish. When we go to system evaluation, here we have system evaluation, which focuses on technical performance metrics such as sensor accuracy, data transmission, reliability. Then we have system uptime. Then we have system evaluation, whereby under system evaluation, it measures classification accuracy and overflow prediction. Then operational evaluation compares optimized routes with traditional routes, hence reducing the fuel. Then we have results, how improved prediction accuracy, which reduces the travel distance, lower fuel costs, and faster collection times. Then these are our expected outcomes, whereby we have reduced overflow incidents, we have environmental, which increases recycle rates. Then we have social, improved public health, community engagement, then scalability. Finally, the conclusion, whereby the step forward smart sustainable urban waste management in Uganda. We included the IoT, then Edge AI and cloud analytics. The system transitions waste management from reactive to predictive. Then we have the future work, whereby large-scale pilot with KCC integration with informal waste pickers and advanced AI models. Thank you.